plots and data interpretation. We're going to be covering this for those of you who couldn't make it to the third bioinformatics workshop for LQB385. And we're going to start off with answering why should you care about plots and data interpretation? Fair enough. I like to think of it as a way to make the complex simple or making the vague clear. You're not going to go and show somebody a whole data table of times and temperatures. If you're trying to explain to them how the temperature changes over a full day, you're going to take that and you're going to turn it into a plot to help them understand stuff easier. That's the whole crux of it, communication. And if we're being honest with ourselves here, a lot of the times when scientists are reading papers, they're literally skipping to the plots and to the figures to try to get an idea of what is actually going on. So when do we want to actually use a plot? In my opinion, we should be using plots when the data has become too complex to explain through words. So if we're going to give a specific example, we'll start off with the sunflower seeds attracted 20% more birds than pumpkin seeds on Sunday. So that piece of information is fine enough to just have as a single sentence. No issues going on there. However, if you're starting to see sentences that look something like this, on Monday there was 327 kookaburras, 121 blue jays, 7 cockatiels. On Tuesday there was 265 kookaburras, 21 blue jays. You're kind of getting the point. This paragraph should be a plot something like this. A lot easier to read, a lot easier to actually get a handle of what's going on, rather than just a block of text. So, now that we're going to use a plot, what are the things that we actually use to determine which plot or graph to actually use? I think that comes down to about 3 different factors. First factor, what do you want to find out about your data? The second thing, what is the type of data that you have? And finally, what are the variables or groups that make up your data? A variable or a group are what makes your samples different from each other. So like age, sex of the patient, the time of collection of your sample, things like that. So if we start to nail down a little bit deeper into the specific data types, it comes into 2 broad categories. The first being numeric, the second being categorical. When we look more into numeric data, it comes into 2 broad categories again. The first being continuous and the second being discrete. So continuous in terms of it can always continuously be found to be more accurate is how I like to think of it. So like temperature or distance, you can be infinitely more accurate about measuring those, so therefore those are considered continuous. Discrete is where your numbers are discrete from one another, meaning that you can't have it be anything in between. So for instance, like you can't have both a living human and a dead human. They're either going to be alive or they're going to be dead. They're not going to be in between. Where this is in a fantasy world where we can have undead zombies. Or like a functioning light bulb or a non-functioning light bulb. It either emits light or it doesn't emit light. There is no in between. Moving on into categorical data, that also comes down into 2 broad categories. The first being nominal, where you have options to choose from, and then even further down from that is sort of ordinal, where it's like a voting system or a ranking system, kind of like those tier lists that you might see on YouTube. Particular aspect about your data that you're probably going to want to look into is your data's distribution. A data distribution, if we're asking for my opinion, is a description of how your results have grouped or not grouped together. But if we go ahead and ask ChatGPT, That one says that a data distribution refers to how data values are spread across a range of possible outcomes, showing the shape of the data when graphed and analyzed statistically. So a bit more of an abstract decision there, but sort of brings in the idea of graphing. And if we ask just regular Google, it says a data distribution is a graphical representation of data that was collected from a sample or population. Once again, bringing that sort of graphical representation in. Overall, if we're trying to collate these answers, we get that data distribution is a graphical representation of how our results have grouped. A distribution in its simplest and most common format would be considered a normal distribution, like an example that we have here. It's got a singular mean and it's got a nice curve, even and continuous on either side. And this is normally done with histograms, with one of your lower x-axis having your variable. So in this one would be test scores, and then the frequency of that score appearing being on the other axis, giving you that nice mean and even distribution outwards. If we were to go on to another one, but maybe when we have a normal-ish distribution, but it's leaning to one side, that one's called a skew distribution. And if it's got the tail going off to the left-hand side, that one's called a left skew, so the shallower side, with the steeper side being on the right-hand side, that one's called a left skew. And if it's the other way around, with the tail or the shallower side being on the right hand side and the steeper side of being on the left, that's called a right skew. Just to give you a point, you're never going to see that these means look this perfect unless you're like in biology, at least. Maybe if you're in physics or chemistry, you might start seeing means or distributions that look like this, but don't expect to see anything this pretty in regular biology. Another example of a different distribution might be where you have multiple means or multiple peaks. So let's say, for instance, you have something like this, where you've got two peaks going around and they're about the same. We'd call that bimodal. Bi meaning two modes, two means even. Or not two means, but two modes where you've got two common peaks. And they're symmetric, so they're about the same. Also, you can have it where it's bimodal, but the two differences, the two modes are different. So it's sort of non-symmetric rather than symmetric here. And one of my favorite ones after that being just a straight up uniform distribution, where across all the samples it's just a flat line, a classic. So the next thing you might be asking yourself is, why do we care about these distributions? What can they actually do for us? What is the point? Well, distributions are very important for two reasons. It gives you some great initial interpretations on what might be going on in your data. So, for instance, if we have a distribution, something like this, of like frog weight, where it's got that bimodal distribution going on, we can see that there's something interesting going on here. Now, that might be down to the species. Maybe this pond has two different types of frogs, or maybe this is just a sex difference between male and female. But at least it lets you know that, hey, there's two distinct populations of frogs in here, and you're probably going to have to treat them differently in your analysis. So that's one initial reason why you want to look at these distributions, is just sheerly to have a initial interpretation of what's going on. The other reason that you want to be running these distributions is so you can check to see if your data is actually a normal distribution or not, because that informs what statistical tests you're going to be using on your data. If it's a parametric test, that means that it is assuming that it is a normal distribution data that it is working with. If the test you want to use is non-parametric, that test doesn't assume that your data is a normal distribution. You can use non-parametric tests on normal data, but you can't use parametric tests on non-normal data, because parametrics specifically assume that your data is normally distributed, whereas parametric tests don't have that at all. So that's the second reason why you want to be looking at the distribution of your data beforehand. We're going to run a little game that I like to call Is It Normal? Essentially, I'm going to show about 3 plots, and your goal is to try to determine before I tell you if it's a normal plot or not. So feel free to pause and think it through and then unpause to get the answer. We're going to start off with this one. Is it normal? Pause now. And no, it's not. Wait. And yes, it is. This one is rough. This is probably as far as I would go, but I would definitely call this one at the end of the day normal. If it was any rougher or any more uneven, then I probably wouldn't call it normal. So this is probably the extent of normal I would go. All right, next one. Is it normal? Pause now. And no, this one isn't normal. This one is bimodal because it had the 2 peaks there. And bonus points if you put non-symmetric for the non-symmetric mode peaks. Last one. Is it normal? Pause now. And no, this one also isn't normal. This one is skewed, and bonus points if you got left skewed because of the shallower tail going off to the left there and the steeper going off to the right. Okay, good stuff. Now we're going to get into some specific plots now. Some very cool stuff. Here we go. So first off, we're going to be looking at histograms. We're going to be looking at scatter plots. We're going to be looking at box plots, correlation plots, and heat map. Histogram is a very useful little plot, particularly for finding out distributions, and the ones we were talking about just before. But it needs numeric data on both axes, so continuous or discrete on both axes. One example you might want to think if you're trying to figure out what you can use a histogram for would be like if you're trying to cook briskets for your family who's coming over for lunch and you're trying to figure out what like cook time you're trying to do. So maybe you cook briskets at different times, like between 1 hour and 16 hour, and then you have your family vote on what their favorite cook time was. And then you can put that all together in a histogram where you have the cook time on your x-axis and your votes on your y-axis to get yourself a nice little histogram there. I like this little plot here. Box plot, I would think to be one of the most versatile plot types that we have. You can have it's essentially like a mean comparison between a whole bunch of different conditions. So you've got yourself your little box there where you have your mean in the center, and then you can represent your standard deviations on either side with the top line, bottom line, and then the extended line. That can also be the different quartiles as well. So you have to like look at the figure legend to figure out what they're going on with there. And then the individual dark dots above and below are considered outliers. They're very good because you can have so much different types of information, like your categorical, your mean, your discrete numeric, your binned continuous numeric. And it allows you to do a whole bunch on a lot here. So like if you had some very complex data, like maybe you were ranking or trying to figure out couples satisfaction in their relationships, and you were like asking them to rate their satisfaction with their relationships like from 1 to 100 under different conditions. So maybe morning, evening, night, whilst their partner is present for be a bit spicy, before and after eating to see who gets hangry or not, and like before and after the anniversary to really see who did like a good job and stuff like that. So box plots got to be one of my favorite plots here. Very useful, very versatile, very good for comparing means and standard deviations of a lot of different populations. One of the particular plots that I've used a whole lot would be considered a scatter plot. And in particular, the reason why I've used a scatter plot a lot was because I was trying to get a correlation between factors for one of my own studies where I was looking at pressure ulcers, and I was looking at how much protein is within the pressure ulcers under different conditions. One thing you'll need to learn about academics is there's nothing they like more than talking about themselves, and I come under that category as well, so you might have to hear me drone on about my work for a little bit here, sorry. So what I would do is I would take the different proteins and I'd measure their abundance, And then I'd also get the what we call a push score. And essentially that the push score, you can just think of it as like how bad the pressure ulcer is. So 0 meaning that the pressure ulcer is like basically healed and good, and then up to 14, which essentially means the limb's about to fall off. But you can get up to 7, which is like pretty severe. So essentially what a scatter plot can do is it can allow you to do a correlation analysis. So it lets you say, how much does my X variable go up? How relating to how much does my Y variable go up? So in this situation, it's essentially how high does the push score go, and then how does the abundance change? So it doesn't have to be positive to positive. So like if you got a positive push, then you get a positive abundance. It can actually be the other way around. So as your push gets worse or your pressure also gets worse, the amount of that protein in particular might be getting worse. So that could be like what we call a negative correlation. And you're essentially going to get two numbers from this sort of analysis. You're going to get what we call an R coefficient, which essentially tells you how tightly linked your two variables are. So how related is the positive movement of your x-axis going to move up your y samples. So if you've got how tightly linked is it going to be? It's kind of like sun exposure and temperature is going to be very strongly linked, so you'd have a very large R coefficient. With your R coefficient going from +1, meaning like it's exactly correlated, to -1, meaning it's exactly negative correlation. And with 0 meaning no correlation, so there's nothing going on, with +1 being this a very, very strong result for a strong positive, and a -1 being a very, very strong negative correlation. Another value that you want to get out of this is your p-value. So that essentially tells you like how significant your result is, the classic p-value that you can expect to find. The data that you can use on this can be continuous numeric or discrete numeric. Measure of your R coefficient. I'll go through that in a bit more detail now. And what the number of ranges I'm going to give you now also work in the negative. So if it's less than 0.1 for your R coefficient, there's no correlation at all. And that also goes for -0.1 to 0. That's also no correlation at all. However, if we got a 0.1 to 0.4, we consider that a weak correlation. That's probably what you're going to get most in biology. Or one step above that is 0.4 to 0.8 being a moderate correlation, and the highest there being 0.8 to 1. I don't think I've ever seen anybody with a 0.8 to 1 in biology, but we can hope, huh? So the next one we're talking about here is a correlation matrix, which follows along from the scatter plot where we got that R coefficient here. This essentially takes all your different variables that you're looking at and then finds the correlation coefficient, that R number, between all of the different samples there. So if we're going, for example, maybe we're talking about like a pumpkin patch and we're recording a whole bunch of different things like soil pH, how much water is there, how much sunlight is there, maybe the available nitrogen, and then we want to try to see if there's the correlations between all of the different factors in one plot. We're going to use a correlation matrix for that, where you have all the different variables lined up on both axes, and then at the intersection on the grid, you're going to have that R number there, and you use color possibly to represent how strongly correlated those were. Now you can expect to see a perfect correlation here between along the 45, because all of your factors are lining up with themselves. So of course it's going to be perfectly correlated with themselves. But what you can also see is that along that 45, it's mirrored as well. Now the reason for that is if you're looking at water correlating with soil pH, that's going to be the same as soil pH correlating with water. So that's going to allow you, it's kind of like a 1 plus 2 equals 3 is the same as 2 plus 1 equals 3. So that's why along this 45, you've got that mirroring effect there. But very useful if you want to look at a whole bunch of different R coefficients instead of a whole bunch of correlation plots. Allows you to move a bit quicker through your data and pick out variables that you want to look more deeply into. we're looking at here is going to be a heat map. This is very interesting to me because it gives you an almost a 3D effect in terms of your plot on a 2D surface using color rather than moving out into the third dimension. It's good because you can use a mix of categorical and numeric. And say, for an example, maybe you're traveling and you're trying to pick out between four different countries, and you're trying to figure if you want to go in summer and winter, and then on top of that you want to figure out how expensive stuff is going to be. So let's say, for example, Philippines, Japan, Egypt, and Canada, and then you got your summer and winter, and then you use color to represent how expensive it's going to be. So in this example, it would be the lighter blue, the or the more expensive it's going to be, sorry, and then the darker blue, the less expensive it's going to be. So that way you can represent so many different conditions, and then you can use color to help you differentiate between the information. So that way you could quickly see that in Egypt in winter would be cheapest, and then Japan in summer being the most expensive. In this example here, very useful. But don't use it too many. A lot of the time when people have heat maps, they have hundreds of conditions against another hundreds of conditions, and I don't know about you, but I find that difficult to read and understand. Okay, so going to do a quick run through on some practice code so that you might find a bit easier to get through this bioinformatics exercise. We're going to be running our code in this website here. It's just a handy website that runs our code online so that we don't have to run it ourselves in our own website, in our own little software. But if you do know how to run this sort of stuff on RStudio, for example, feel free to give it a go. Then we've got part A here, which is going to generate our data set for us. So similar into the code for the questions, you're going to have part A be the code to generate the table. And then part B, or the other parts, are going to be the code that generates different graphs. So you're always going to have this part A as the top part in there, and then you're going to select which plots you want to use underneath. So we're just going to go ahead and copy all of this to start with. And in this one here, you can just paste it all in there. And then once you've got all of this in here, you can run. So in this example here, we've generated a nice box plot here with the different types of chocolate down there. But instead, I'm going to want to change it so that instead of running the chocolate for the different types of chocolate, I want to have a look at the different brands. And we can see here in our data set that it generated a brand for each of our chocolates here as well. So we're going to copy this here, and then we're going to go down into and change out chocolate type for chocolate brand in here. So it's the exact same process for the full questions as well. You can find it'll mostly just be changes like this, where you're just changing your X and Y values to reflect something, to reflect the gene you're wanting to run. And then we'll run it here. And there we go. It's changed it out from chocolate amount and chocolate type to chocolate amount and chocolate brand. All right, so it's pretty much exactly that. Good luck with the questions.